Welcome to The Explainer, brought to you by Forge College. All right, grab your safety goggles and roll up your sleeves because today we're heading straight into the workshop. We are tackling implementing core modules. This is basically the pivotal capstone moment in our Inheritance and Interfaces in Solidity course, right here on the Solidity from Zero track. Now, I hope you're feeling a little bit like a mad inventor today because we're finally going to build our very first working, humming, smart contract machine. Let's get to it. Here's our assembly manual for today's explainer. First, from blueprint to reality. Then, setting up the scaffolding, fabricating the core components, wiring the business logic, compile, test, and verify, and finally, blueprint for next steps. Okay, let's dive into this. Section 1, from blueprint to reality, tracking our engineering progress. So before we fire up the compiler, we really need to know what we're building, right? You wouldn't just start welding pieces together without a schematic. Think of Lesson 1 as the months we spent designing the high-level model map, really understanding the requirements, the upgradability, and the acceptance criteria. Then came Lesson 2, which was like the weeks we spent drafting the precise interfaces, mapping out exactly which functions go where. But today's the day we hit the shop floor. We are machining the concrete parts. We're taking those interface shapes and turning them into actual executable Solidity code. The goal here isn't a final polished product just yet. Nope, it's to create working code increments that prove our design isn't just, a fantasy. Moving right along to Section 2, setting up the scaffolding, building the physical workspace. You just can't build a precision machine in a messy workspace. Seriously. So, whether you're using Hardhat or Foundry as your toolchain, the absolute first step is strict physical organization. You're going to create a new directory. Let's call it Capstone Core Modules. And inside your contracts folder, you absolutely must create two distinct subfolders, one named Interfaces and one named Modules. I literally cannot stress this enough. A tidy workspace prevents the compiler machine from throwing sparks later. Our testing tools need to know exactly where to find the blueprints, the interfaces, and exactly where to find the heavy machinery, the modules. All right, Section 3, fabricating the core components, machining storage, and access control. Okay, so with our workbench perfectly organized, it's time to fabricate. We're going to machine our first two isolated components, so they perfectly match the specs we designed earlier. And honestly, this brilliantly illustrates the core philosophy of our entire build. Over on the left, we've got the interface stub, istorage.sol. It's really nothing but a lightweight blueprint. It basically just says, hey, I have a set function and a get function, and that's it. Then, on the right, we have the concrete implementation, storage.sol. Now, this is the actual machinery. It imports that blueprint, it contains the private state variables, and it holds the actual internal logic that does the heavy lifting. The cool part? Other contracts will only ever look at the blueprint on the left, but they'll secretly be interacting with the working machine on the right. Let's take a closer look at the specs for that storage module. It's delightfully simple. We've got a private state variable holding our data. We use external visibility for our set and get functions to match those interface expectations perfectly. And, crucially, we include the glorious override keyword. Listen, if you tell the compiler you're implementing an interface, you absolutely must use the override keyword on those functions. Forget it, and I promise you the compiler will instantly start complaining and blowing smoke right in your face. Next up, we fabricate the AccessControl module. So inside AccessControl.sol, we just maintain a simple mapping of addresses to booleans to track who exactly is an operator. Our constructor grants operator status to whoever deploys it, and then we expose two functions, setOperator to mutate permissions and isOperator for other modules to check them. Notice how minimal we're keeping the surface area. We aren't adding any complex role hierarchies or anything yet. Why? Because we want our initial unit tests to focus purely on the structural integration of the machine, rather than getting totally bogged down in policy complexity right out of the gate. Which brings us to Section 4, wiring the business logic, assembling the orchestrator motherboard. Now that we have our isolated parts fabricated, it's time to bring in the motherboard. We're wiring up the business logic module, which acts as the central hub orchestrating these separate components. And the secret sauce here is dependency injection. In smart contract engineering, this is the literal physical wiring of our machine. See, instead of hard-coding the exact location of our storage and access control contracts right into the business logic contract, which would, permanently glue them together, we pass their addresses in through the constructor. This is huge. It means we can easily plug and unplug different components, or even use fake mock components for testing, without ever having to change the motherboard itself. It's honestly the ultimate flex in modular design. So here's how that business logic wiring actually looks. The contract imports iStorage and iAccessControl. The constructor receives two addresses and casts them to those interface types. This means our orchestrator is compiling against the universal interface plug, not some rigid concrete type. Finally, we build an only operator modifier. Now, whenever someone tries to call a state-changing function, this modifier reaches out over the wires to the AccessControl module, asks is operator MSG.sender, and either allows the call or just brutally reverts it with an error. Let's power this up. Section 5, compile, test, and verify. Powering up the machine.
Okay, the scaffolding is up, the parts are machined, the wiring is completely connected. It is time to flip the switch. We are powering up the machine to see if it actually works by initiating our fast compile and test cycles. And a successful power-up diagnostic looks exactly like this. First, we run npx hardhat compile or forge build. The expected result, 0 compiler errors. Boom. Second, we verify our interface signatures, which means absolutely no typo error or override mismatch messages. Finally, we run a minimal unit test. We deploy our contracts in memory, grant an operator status, call our store function, and assert that reading it back gives us the exact correct value. If all 3 of these diagnostic checks pass, congratulations, you have successfully built a functioning, modular smart contract system.
But, what if it doesn't pass? What if the machine literally starts smoking? Seriously. Don't panic. Compiler errors are a totally natural, even beautiful part of the failing fast methodology. Here are the most common sparks you'll probably see. Import path errors. Always double-check your relative paths. A module importing an interface usually needs a .interfaces/path. Missing override keywords. We joked about this earlier, but it happens all the time. Visibility mismatches, like maybe having an external function in the interface but accidentally making it public in the contract. And finally, constructor wiring failures, where you just forget to pass the required addresses when deploying your test dependencies. Just isolate the failing behavior, fix the spark, and recompile. You got this.
Section 6, Blueprint for Next Steps, Securing the Final Artifacts.
Before we clean up the shop and prep for the next phase of our capstone project, I really want you to remember our golden rule. Interface first reduces coupling. By depending on iStorage and iAccessControl instead of the concrete implementations, you have preserved your absolute freedom. Think about it. You can swap out how storage works tomorrow and the business logic won't even blink. You can test your smart contracts in total, complete isolation. This is literally the secret to building massive, complex Web3 systems without them just collapsing under their own tangled weight. So, before you move on to the upcoming integration testing and security checks lesson, you need to complete this specific checklist. Number 1, commit your 3 module files and your 3 interface files to your repository. Lock them in. Number 2, write those minimal cross-contract unit tests deploying your dependencies in process. And finally, list out the invariance and acceptance tests you recorded way back in lesson 1. We're definitely going to need those to write our integration test cases next. Because let me tell you, once the machine is built, the real fun begins. I'll leave you with this provocative thought. How will you intentionally attack the surfaces of your newly wired machine? Because in our next explainer, we aren't just going to use it, we are going to try to break it. To dive deeper into security-oriented assertions, integration testing, and tons of other advanced Web3 topics, be sure to visit forge.college. On behalf of Forge College, keep building, keep testing, and I will see you in the next explainer.